Solar power is taking the world by storm, as experts have said that it could match coal prices. Among many of its benefits, this renewable energy source aims to reduce electricity bills, decrease pollution, and advance technological development. But how does this all work? Stay tuned to find out.
The main ingredient in any standard solar panel is called silicon. Silicon is a semiconductor, and it has 4 valence electrons, which allows its atoms to arrange themselves in tight crystalline structures. Silicon is also the second most abundant element on Earth, which makes it easy to obtain for manufacturing purposes. As mentioned before, silicon is a semiconductor, not a conductor. Therefore, it does not facilitate an electric current very easily on its own. However, solar panel manufacturers have their ways. Doping refers to the process of intentionally adding impurities to a semiconductor in order to increase its conductivity. For example, when an element like phosphorus with 5 valence electrons, one more than silicon, is added to a solar cell, 4 of those valence electrons are shared with 4 more electrons from 4 other silicon atoms. Thus, 4 covalent bonds are formed and the phosphorus atom's octet is filled. However, 1 electron is left to move about freely, creating a negative charge. In this case, phosphorus is referred to as the donor dopant because it donates an electron. Similarly, when an element like boron with 3 valence electrons, 1 less than silicon, is added to a solar cell, a positive charge is created because there is an absence of negatively charged electrons. We call these point positive charges holes because they represent missing electrons. In this case, boron is referred to as the acceptor dopant.
Solar panels are composed of 3 main layers. On top, we have the negative type, or N-type layer. This is the layer where phosphorus is added and negatively charged electrons are released. On the bottom, we have the positive type, or P-type layer. This is the layer where the boron is added and positively charged holes are created. The thin layer in the middle, where negative and positive meet, is called the p-n junction. The most important thing to remember about the different charges of the layers is that electrons and holes can move. This means that the negatively charged electrons, which were originally released in the N-type layer, do not all stay there. In the same way, the positively charged holes which were created in the p-type layer do not all stay there. In fact, in the p-n junction where opposite charges meet, the negatively charged electrons are attracted and move closer to the p-type layer, while the positively charged holes move closer to the n-type layer. The result is actually a net positive charge in the n-type layer because, since the free electrons of the phosphorus have left the layer, only the phosphorus atoms are left, locked in formation with the other silicon atoms. Phosphorus has 1 more proton than silicon. Now that its 5th electron is gone, it contributes a positive charge. Similarly, in the p-type layer where boron is locked in formation with other silicon atoms, a net negative charge is created because boron has 1 less proton than silicon. The result is an electric field in which electrons are actually drawn toward the formerly negative type layer. The stage is now set for electricity production. When powerful radiation from the sun is absorbed by a solar panel, electrons are knocked free from the silicon. Because of the electric field, these newly freed electrons are drawn upward through the N-type layer, where they funnel into a metal wire. This metal wire is connected to your house, or your car, or a phone, or whatever you're powering with solar energy. Finally, a wire comes out of your house or phone or car and goes back into the solar panel, thus completing the solar circuit. This flow of electrons is called electricity, and it's all made possible by, you guessed it, chemistry.
The silicon used in solar panels is a crystalline solid. As such, each of its atoms behave very similarly. The bonds between them are of the same strength and require the same amount of energy to break. This being said, common dopant atoms such as boron and phosphorus are similar enough to silicon in electronegativity that they can pass for silicon atoms and bond into the crystalline solid. Crystalline silicon is a covalent network solid. Covalent network solids are usually defined by their hardness, strength, and high melting points because they are networked full of covalent bonds. The Lewis structure of this matter would mostly be a silicon to boron covalent bond and a silicon to phosphorus. Each boron and phosphorus atom shares an electron with 4 other silicons. The boron to silicon causes an empty hole, creating a positive charge, whereas phosphorus to silicon forms a negative charge due to the presence of an extra electron. As we explained a few moments ago, this structure causes the doping effect. The action all happens when thermal energy hits the solar panel. The 5th electron of phosphorus, the one that is not included in the bonds with silicon, is only weakly attached to the phosphorus atom. It's so weakly attached, which is around 0.045 electron volts bonding energy, that at normal temperatures, the thermal energy within the crystal is sufficient to free it from the phosphorus atom. Due to the specific makeup of a solar cell, only electromagnetic radiation between the wavelengths of 350 to 1140 nanometers is absorbed. This includes the visible light spectrum, which goes from about 400 to 700 nanometers. Ultraviolet radiation, which has very short wavelengths, does not make it into the solar cell, while infrared radiation, which has very long wavelengths, passes right through.
Standard testing conditions, or STC, for solar panels maintain that the sun emits 1.0 kilowatts of energy per square meter, and that the solar panel is kept at 25 degrees Celsius. Most solar panels have efficiency ratings of around 15 to 18%. Let's assume that you have 250 square meters of available roof space, a little less than the average size of the roof of an American home. To calculate the average power output of your solar panel array, we first multiply 250 square meters by 1.0 kilowatts over 1.0 square meters. The trailing zeros allow us to maintain calculations with 2 significant figures. This will tell us how much power the sun is emitting in kilowatts. To convert this amount to watts, we can then multiply it by 1.0 times 10 to the third watts over 1.0 kilowatts. This tells us that the sun is emitting 250,000 watts into our solar array. Unfortunately, however, solar panels are not capable of converting most of the sun's energy into usable electricity. In fact, solar panels on average are only about 15 to 18% efficient. In order to get a rough estimate of the power output of your solar panel array, we can then multiply our 250,000 watts figure by 0.15, our low estimate, and 0.18, our high estimate. Our estimated power output comes out to be somewhere between 38,000 and 45,000 watts.
So why is solar energy important? Although solar energy has limitations such as being unreliable or not working on cloudy days, and efficiency levels being relatively low, only about 14% to 25%, the costs of solar energy have dropped to as low as 75 cents per cell. New technologies have made solar power increasingly efficient and have led to clean power, resulting in no emitted greenhouse gases. Our future is renewable energy. Our future is solar.